Alright, what's up guys? In this video I'm going to pick up some multivariable calculus, and we're going to be talking about double integrals and polar coordinates again. So we're just asked to evaluate this double integral by converting it to polar coordinates. So we're given the double integral here, 2x y dA. It says that D here, which is our region, is the portion between the circles of radius 2 and radius 5, centered at the origin, and it lies in quadrant 1. And what I've done is gone ahead and taken care of the graph for you. Okay, so for polar coordinates, let me just remind you. So remember, for polar coordinates, x is equal to r cosine theta, and y is equal to r sine theta. And then r squared, remember that's equal to x squared plus y squared. And if r squared is equal to x squared plus y squared, then that means that r is equal to the square root of x squared plus y squared. In our particular circumstance, we know we're going to convert this to polar coordinates. Now we're given circles of radius 2 and radius 5. So we know what the range is going to be for r, and the range for theta in this particular circumstance, if we're dealing with a circle, is going to be from 0 to pi over 2. So we can go ahead and write down the region and basically get that out of the way. So it's going to be r comma theta, and since we got radius 2, radius 5, that means that the range for r is going to be from 2 to 5. And since it's a circle, again, the range for theta will be from 0 to pi over 2. So those are our ranges there. Okay. Also, remember that this is a very common mistake with polar coordinates. Remember, dA is not equal to dr d theta. Not equal to. So I'll put a big old not right beside it. It's very important that you know that dA is not equal to that, because some students will do that. They'll think it's dr d theta. Remember that dA is r dr d theta. Very, very, very important there to memorize that, because I guarantee you that'll get you. It got me one time when I was in Calc 3. So please make sure that you take note of that r. I guess I'll put a big old X beside it. That way you'll know that not to make that mistake. Okay, so let me get another sheet. All we got to do is convert the integral to polar coordinates, which we've done before. I did an example like this not too long ago. Alright, so we got our double integral that we were given. Again, D is the region. We got 2xy dA. So remember, it's going to be r dr d theta. So that means we're integrating respect to theta last. So the limits of integration for the outermost integral will be from 0 to pi over 2. It'll be from 2 to 5. And then we'll stick in everything. So it'll be 2 multiplied by r cosine theta, multiplied by r sine theta, multiplied by r dr d theta. All right, let's clean it up a little bit here. We can make use of our double angle identity, because remember that sine of 2 theta, that's just going to be 2 times sine theta times cosine theta, and r times r squared is going to be r cubed. So we'll have the integral from 0 to pi over 2 from 2 to 5, and we'll have r cubed sine of 2 theta dr d theta. Now it's just a double integral, so we'll integrate respect to r first, treating theta as a constant, and then we work our way innermost to outermost. So this would be from 2 to 5. So this is what you should be looking at. Okay, so theta here is a constant, so it can come out. So we get sine of 2 theta. The antiderivative of r cubed is r to the fourth, so this would be r to the fourth over, it's not r to the fourth, r to the fourth over 4. Let me be more correct there. And then we plug it in. So we got sine, stick in the 5. That's going to give us 625 over 4, I believe. I'm pretty sure I'm right on that. And then 2 squared is, 2 to the 4th is 16 divided by 4, so this would be minus 4. And I'm going to check, by the way, just to make sure I'm not off on that. Yeah, I'm not. So let's say we get 609 over 4. Now what we need we'll need is we need to multiply our sine of 2 theta times 609 over 4, but 609 over 4 is a constant. So we'll pull that out, and then we'll have the antiderivative from 0 to the power over 2, and we'll have sine of 2 theta, d theta. Now, if you don't know how to integrate this, I guess I'll show you. Do a u substitution. Pick u to be 2 theta. That means that du is 2 d theta. And we'll get 1/2 du is equal to d theta. So we'll have 609 over 4 multiplied by 1/2. We'll have to change the limits. So this would be sine of u du. Changing the limits, u was 2 theta, so that'll be 2 times 0, which is 0, and then 2 pi over 2. And you basically just substitute in to get your new limits, and this obviously gives us pi. If we take the antiderivative of sine, we get negative cosine, and then we can simplify the constants on the outside, which give us 609 over 8, and then this will be negative cosine of u, and it'll be from 0 to pi. Alright, so cosine of pi is -1, but since we got a negative there, it's going to be 1 minus, and then cosine of 0 is 1, but we got a negative there, so this would be 1 minus -1, which you know is 2. So then we got 609 over 8 multiplied by 2, which gives us 609 over 4, which is our answer. So our final answer for this double integral over in polar coordinates is going to be 609 over 4. And that's your answer. All right, that's going to be it. So let me know if you got any questions. And I'll see y'all next time.